We really appreciate you coming in today. We have a great show to show you, an amazing class here, and really don't want to take up too much time before we let them demonstrate the skills they've learned in this training. Really what I want to try to summarize are two things. The first thing is why you might want to be here. A lot of times I get that feedback. If you don't explain why someone would want to be at a demo, then they sit there and go, why am I here, right? The first reason is if you look at our training schedule or listen to their demonstration, you can hear about the project-based training that we offer at LHBU. And if you think about someone in your team that might need that, feel free to get a hold of us through lhbu.com or through Aaron Hartman or someone else at LHP, and we can get your person lined up and put through the training. The second reason is obviously these people have the skill set necessary to control and run a diesel engine at the end of this class, and they will be available for work on Monday. So, and I'm pretty sure most of them are willing to go just about anywhere, so there's no real travel restrictions at all. So if you have any team needs in the resource area, that's why you have the resumes. The second topic that I want to cover before I turn it over to the team is just kind of the advancements that LHBU has made through this 4-year process, and kind of where we're going from here. So one key advancement is the packet that you see at your desk. Again, Pam was hired about 3 months ago and has made a tremendous impact to the organization of LHBU, as you can tell just by the organization of the packet and a description of what you're going to go through today. Some other things just to update you on are the classes that we're going to be running in 2016. So we don't just have a 6-week diesel boot camp, we also have a 6-week gasoline boot camp. And we have the negotiations. Are they done yet, Dave, for the facility in Detroit, or are we pretty close? The facility in Detroit?
Is it done? Good question.
Okay. So in 2000...
I got the final word that it's signed, sealed, and moved.
So you can expect a facility in Detroit in 2016 where we're running the gasoline version. Once again, we did that last year. The other thing is our powertrain calibration course, which we've partnered with SAE on, that'll be rolled out in 2016. It's a 1-week hands-on project-based powertrain where they calibrate an engine and they calibrate a transmission. So those are exciting classes. The last offering to talk about before I turn it over is the e-learning environment, or what we call the remote training. So we are in development of the remote training. We have already recorded content. We already have the remote project. And essentially what you can think about in terms of the e-learning environment is, how do I get someone trained in this environment, maybe not as well with having a hands-on instructor every day, but they can learn the skills from a remote location. So it cuts down on the amount of time they have to spend specifically on the project and allows them to continue working on their daily job. So those are the main updates, and now I'd like to turn it over to the team.
Thank you, Zach. Good morning, ladies and gentlemen. My name is Ochuko, and I recently completed my bachelor's degree in mechanical engineering from the University of Illinois at Urbana-Champaign. I am one of 14 team members that recently completed the Fundamentals of Diesel Engine Controls course run by LHB. So our objective of this course was to actually develop code in MATLAB and simulate code generation in order to successfully run a real-world diesel Cummins 5.9 liter engine with the VP44 fuel injection pump. Like I said, we're 14 engineers, we're from 4 different countries, 12 different universities, and obviously there were some challenges that we had to overcome in terms of a language barrier, different backgrounds, but we're able to effectively overcome all that, work together as an efficient team, and we were able to successfully complete our project. So, like I said, there were some challenges, one of which was the fact that the engine did break a record number of times, which is 4. So yeah, but at the same time it was a great experience because we also increased knowledge of testing and calibration and diagnostics as well. And we were able to fix all the problems with help from, of course, Rick and as well as an employee from Cummins. So that was a great experience as well. And as if all this wasn't enough, we actually do end up getting an SAE Certificate of Controls Mastery at the end of the course. So it's just like piling on the greatness and awesomeness of this course. So I would just like to thank LHB for the opportunity and just acknowledge some of the partners without whom this course would not have been possible. So this is a general overview of the presentation we'll be giving today. We'll first talk about the kind of like an overview of the engine that we'll be working on, which is, like I said, is the Cummins 5.9 liter diesel engine. And then we'll kind of go into different aspects of our project, which include the sensors and the actuators, and as well as the controller that we actually built in order to run this engine. And then we'll talk about how we were able to send these messages and communicate with the engine through CAN, J1939 in particular, as well as the MotorHawk blocks in Simulink. And then lastly, we'll talk about how we're able to test and validate our design and our model that we built. So basically, verification is important because you don't want to break the engine again. So we'll talk about kind of how we did that using the DTE, and then we'll have a conclusion, and then we'll lead you out for some demos. So obviously, like I said, the objective was to successfully code in MATLAB and Simulink in order to run an engine. So now I'll hand it over to Kavya, who's going to explain the working principle of the engine. Thank you.
Thank you, Hugo. Hello everyone, I'm Kaveshri. I've done my Masters in Mechanical and Aerospace Engineering from University at Buffalo. As Ochiko said, running engine or controlling a diesel engine is our goal. That is what we had in mind when we came here. But initially we wanted to know how this diesel engine would work like and what are the things we have to control. So here is just a basic or typical how a model of 6-cylinder diesel engine look like. And here on the right side we have how a single cylinder would be working. I assume that you all would be knowing that, but let me just give a quick overview on this, where we intake air and then we compress it, and then we will be injecting the fuel at the right time, and then power produces, which runs our engine, and then there's our exhaust. So what are the things we exactly have to control is when to give the fueling, that is the timing, and the amount of fueling we are supposed to give. Here we know what we have to do, and here is how we are going to do the same thing. So basically a control system or complete model if you take, which has two parts, one is the plant model and another one is the controller. So from the plant model we are sensing the data using sensors, and our controller does all the mathematical calculations that we want to do, and our actuator data is sent to the actuator, which puts our plant model in action. So here are the data that we are sensing, which is the engine speed and then the pedal position from the sensor, from the plant, and then we are calculating the amount of fuel that we have to calculate, that we have to give to the engine, and then the actuator does the job of lift pump and the timing of the fuel injection, and we are then calling the plant and saying that, hey, hello, here's my data, so do what the job you have to do. But then this is not exactly what we started on. We wanted to know how exactly this would be working, or we just wanted to have a smaller project which would be telling us what are we going to do later. So for that case, we designed an electronic throttle controller, which will be explained by Sandeep. Thank you everyone.
Thank you, Kavya, for giving the overview of the diesel engine control and also the sensor data and the actual data. Hello everyone, my name is Sandeep. I'm currently pursuing my Masters in Mechanical Engineering at University of Michigan, Dearborn. Coming to the project, we know Axie explained the sensors and actuators should work in a particular way. So we don't know how it works, so we have done a project named Electronic Throttle Control. So coming to its components, analog slider and the controller and the throttle body sensor. Coming to its working, the electronic controller will send a reference signal to the analog slider and the throttle body sensor. The analog slider, when we slide the point pin, when you slide this analog slider, which is connected to a sensor, measures the position of the slider, and it alters the signal to the ECM. The ECM collects the input data and it activates the throttle body motor and also the sensor of the throttle valve. The throttle valve, which is connected as a butterfly spindle valve, it measures the angle and gives the feedback to the controller. So the main function of the controller is to take the inputs from the analog slider and the throttle body and make sure that these two functions accordingly. And how it is calibrated and what are the voltages to be converted will be explained by Manu. Thank you.
Right. Thank you, Sandeep. My name is Manu. I'm a Master's Electrical graduate from Colorado State University. What we see here is we need to read some data off of these instruments, and It turns out that they operate on analog signals. These wiggles don't necessarily have to mean much. So modern electronics has a way to convert them to digital samples, and thanks to Motorhawk, we can read them in really easy ADC counts, mathematical quantities that we can work with and convert into engineering units. Now, in those units or ADCs, the pedal would be going from say 0 to 920, but this might not always be the case. Sometimes we might have some manufacturing defects or something like the plastic limiting the position of the lever or the play of the lever. In those cases, we might want to change our operational ranges to say just this much defined between the blue lines. And this is what calibration is. We make corrections to our readings, and we make corrections to the inputs that we have. And calibration is really important. This is just a simple case where we are retuning our operational ranges, but sometimes they're far more consequential. Right, so the next part is coming back to our engine model. We're going to be talking about sensors, and Jingritsu is going to take over. Thank you.
Thank you, Manu. Hello, everybody. My name is Jingrian, master's degree in electrical engineering from University of Illinois at Chicago. And I'll talk about sensor. As we know, we are all human beings. We have feelings. Machine has feelings too. Actually, they are alive. And I'll talk mainly about two sensors: the pedal position sensor and the RPM sensor. Let's take the pedal position sensor first. Well, I'll introduce about how we build the connection between the real sensor to our Motorhawk model. And we use this analog model to get the count, and we convert the counts, use gain and offsets to convert it to a scale of 100%, and it's better for us, convenient for us to further calculate. And here we go, the RPM sensor. Before definition, we need to figure out how it works, how the encoder pattern works. And we go to the engine room, put the probes to the engine signal, and we get the photo. And we see when there are 35 single pulse, there's a gap. That's to say, there's a 36 minus 1 teeth in the crank. So we know that there's an angle in the intervals, and divided by the duration, we can figure out exactly how many rotates per minute. That's where we definition here in this model, how the 36 minus 1, the single tooth, and the rising edge, the bingo, we got it up here. I'll hand over to Katie. Thank you.
Thank you, sir. Hi, I'm Sankirti. I'm going to talk about control strategy. I'll take an example of this presentation to explain how we did it. Like when we know we have to present what we learned, we just didn't do it in one step. We did it in different stages. Like initially we figured out who will do what, and then we did the slides, and we are doing it today now. And that we did it in stages. In similar way, when we fuel our engine, it gradually starts giving fuel. It gradually speeds up. Like the initial stage is like stall, where the speed is set to be 0 to 100, and the next stage is crank, the speed is set to be 100 to 600, and the next stage is run. And this is the stage where we control the speed, where we control a fuel with the speed and the pedal governor. Like, if I keep on saying this presentation, you guys get bored and you don't even understand what I'm going to say. In similar way, if we keep fueling our engine, it goes on speeding up, and we don't want to blow up our engine again. So now we're limiting the speeds using max governor, idle governor, and pedal governor, and this is being explained by Suyog. Thank you.
Thank you, Kirti. Hi, my name is Suyog. I am a graduate student in electrical and computer engineering at Purdue School of Engineering at Indianapolis. I am going to talk about the controller part. As explained by Kirti, there are three governors, which are idle speed governor, high speed governor, and pedal governor. So, how does a controller decides which governor to be activated? So, if your RPM is below 1900 and you are not giving any throttle input, which can also be below 2%, then your idle speed governor will be activated. Otherwise, it will go on to the high speed governor. So for idle speed governor, we have set a limit of 700 for idle speed, and we are targeting our speed to 700, and the throttle percentage is less than 2%, and we are achieving a smooth curve while accelerating and deaccelerating. Here's our Simulink model. You can see the idle management controller. Here are some logic and mathematical equations in it. This is a PI controller which just increment or decrement according to the orders from idle management controller. It acts as a brain, and this acts as a body part. So here's the graph. The yellow line is the actual speed, target speed, and the violet is the actual speed. And you can see that the curve is pretty smooth, and we are achieving the target speed. The pedal governor is, we are just relating APP with the fuel, like if we are not using high speed governor or we are not using idle speed governor, a pedal governor will be activated. This is a high speed governor which is identical to a idle speed governor, but the mathematical calculations and logics over here are different than the idle speed governor. In this case, the RPM should be greater than 1600, and your APP should be greater than 2%. And we have PI to increase or decrease the speed and set to 1700 RPM. You can see in the graph that from the speed above 1500, it's gradually increasing to 1700 with a smooth curve, with the yellow one as the idle target speed and the violet one as our actual speed, what we got, and the fuel consumption is good. So the next PI controller will be explained by Yin Chan. Thank you.
Thank you. And my name is Yin Chuan, and I graduated from University of Illinois at Chicago for my master's degree of electrical computer engineering. And I'm going to talk about the PI controller. So what's PI controller? PI controller is a control loop feedback mechanism controller trying to decrease the target speed and actual speed, decrease the difference between them by adjusting the fuel injection. So what that means? So basically like you're chasing girls, and according to the girls' reaction to adjust your next move. So how does it work? So the PI controller continually calculates the error value. The error value multiply the P gain to generate the P part, and the error goes to an integral transfer function to generate the I part. By adding them together, you will know how much fuel you need. Let's go back to the story of the chasing girls. Okay. This is you, this is the girl, this is the reaction, this is the current reaction, this is the experience you have. According to these two, you know what's the next move. Right? And sometimes when the engine goes too high or too low, the integral part goes to infinity. So we need a signal to reset this part. So also we don't want to kill the engine, we need a reset value to keep the engine running. And what this means? This means when the girl dumps you, you don't want to stay where you are, you want to move on. You go to the bar, you got a drunk, you wipe it out of the memory. So you start a new life. And now we know how much.
But it is a good application.
Yeah. Now we know how much fuel we need. But how to transfer this fuel from the tank to the engine, I let my teammate Shanmuga explain this for you. Thank you.
Thank you, Michael. That was a very good explanation and comparison between the PI controller and the real life. And hello, I'm Shanmuga. I'm recent graduate from Cleveland State University with Masters in Electrical Engineering. Up to now, we have seen the specifications of the engine we are working on, the sensors, and the controller output, which is the fuel, the calculated amount of fuel which is going to be given for the actuators. And
this is our lift pump. I have to say something about this. This is the guy who created a lot of trouble for us and faced a lot of trouble from our faulty models. And this is the overview of the fuel management system. In motorcycles, we have the fuel tank on the top of the engine, where we can use the gravity to take the fuel from the tank into the engine. But in case of the cars and trucks, it's not going to happen. We cannot use gravity anymore. So we need something else. Here comes the lift pump into action, where it takes the fuel from the fuel tank and then pass it through the chassis filter and give it to the VP44. But it also does a main function in keeping the low pressure among the system up to VP44. And this is our governor model, where we have initially found out the states where the engine is running, whether it is in stall state, crank or run. If it is in stall state, we have given the duty cycle as 100% for the first 2 seconds, just to prime the pump, to bleed the air bubbles outside and send the clean fuel. And for the crank state, we give 50% duty cycle, and for run we maintain 100% duty cycle, and we maintain it low pressure at 6 psi. And the rest of the things will be managed by the VP44 to pump the fuel with the high pressure, and that will be clearly explained by my teammate Tanvir.
Thank you, Shanmuga, for explaining the lift pump to us. Hello everyone, my name is Tanvir. I am a master's student from Southern Illinois University, and I graduated with a degree in mechanical engineering. And now I'm going to explain the VP44 and what it is. Shanmuga just explained the lift pump, that is a low pressure pump that just supplies fuel from the fuel tank to the fuel system. But the pressure is not enough so that we can spray it inside the cylinder. So we need another high pressure pump, the VP44, so that we can attain that high pressure and distribute the fuel inside the cylinder according to the proper firing order. So you can see it's VP44 from Bosch. There are 6 cylinders, so we have 6 outlets, and that distributes the fuel inside the cylinder. So what it does, basically, as I described, it pressurizes the fuel, it distributes the fuel according to the firing order, and also it meters the fuel that we send by pulse. And this is what it looks like. The position of the pump in the engine is on the left side if you look from the flywheel side, and it is driven by camshaft. And you can see the driving shaft that is located just behind the timing gear assembly. It is driven by camshaft, and it is a radial piston pump. It has solenoid valves at each outlet that we control the outlet of the fuel, and it's a distributed style. And almost in all the pumps, there are built-in ECU that communicates with the main ECU of the engine using CAN communications. That is the overview of the VP44, and the rest of the pump, how it is controlled and what we did, will be explained by Ajay. Thank you very much for your attention.
Thank you, Tanvir. Hi, my name is Ajay, and I'm from Arizona State University. I have a master's degree in mechanical engineering. Now going back to the governor. From the governor, we learned how much fuel we need for control to happen. But the question arises, when do we supply this fuel between the cylinders? How do we inject and how do we time? This gives us a cue to the VP44. This is the VP44 and the signals it receives, and the signal that is of specific interest to us is the engine position reference signal. What is this signal? It looks like this. Each of these waveforms is an individual firing event in the engine. There are 3 of these waveforms in rotation of 360 degree and 6 and 720 degrees. And this little dip here corresponds to the engine firing event, which is approximately around 10 degrees after top dead center. And we are going to help inject and time, we need to build this signal all over again. And how do we do it using the Motorhawk blocks? We have something called as the Motorhawk Dual PSP. We use this for injection and timing. There is another challenge. There are going to be only 3 pins on our ECM board that can be used to fire our engine, but we have 6 cylinders on the engine. So what the Dual PSP does is it creates two pulses which can be offset by 120 degrees, and this helps us time the engine. So we give in our engine offsets of 120 degrees. We give the start of injection and the injection duration, and this helps us time. Now, how do we let the VP44 know how much fuel we need to get? I'm going to ask Siddhartha to explain about CAN communication. Thank you.
Thanks, Ajay. Now we have looked at the sensors, controllers, and actuators. So we need some communication to send the control commands from the controller to the VP44 pump. So we have used the controller area network, which allows the microcontroller to talk with the devices in a network. We have a very few devices. The point-to-point wiring is a cost-effective device, but if you have more number of electronic devices in a system, the system becomes very complex. So the CAN is used to overcome this complexity with additional benefits. So we have a error checking mechanism which we can implement in the CAN. We can assign the priorities to our messages. We can send the broadcast communication to the entire nodes, and the complexity also reduces. And the BMW 8 Series is the first car in which the CAN protocol was implemented. And this is the diagram which shows how the CAN bus looks. We have a nodes which are connected parallelly, and the CAN bus signal is represented by the difference between the CAN high and CAN low signal. So if we have any interferences coming from the external disturbances, it affects both the signals, so the effective difference still remains the same. So that is why we use a differential signaling for this communication. And we can also use a shielding to still avoid the external disturbances. This is the cable which we use for our electronic throttle control project, which has a proper shielding. And moving on to J1939, it is a specification which tells how we need to implement our CAN protocol. We can assume that the CAN is a telephone wire network where the J1939 is a language spoken onto the telephone networks. And it allows maximum 30 nodes which can be there, and with 40 meters as the maximum length, and it works on 250 kbps length. And this is a picture which shows the CAN frame. We have a start of files, we have an identifier which we can have a source address, destination address, and priorities. We have a data field where our actual data goes in, and we have a cyclic redundancy checks which we'll use to check the errors, and we have an acknowledgements and end of files. Now we'll see how we actually send our CAN messages, which will be explained by Shashi. Thank you.
Thanks, Siddharth. First, I need to thank you for your time and patience. Well, I am Shashidharan. I did my master's in mechanical engineering from University of Toledo. So today I'm here to talk about the CAN messages. In this presentation, we'll be seeing what and how to send in a CAN bus. So as I said, so we will be sending some information about the fuel, some information about the CAN timing, some information about the ignition, and some information about the synchronization. To make it simpler, just for understanding purpose, in real world we have different languages. So each language is differentiated from the other by using a set of roots. Similarly, we need to differentiate the information. Of fuel from the CAN timing. So we do it by using PGNs with the help of SAE standard J1939. And one more thing is that in CAN bus, we used to have many messages. So out of that, some are critically important and some are not that much important. So we need to prioritize the critically important messages. Otherwise, we will be ending up like this. In this picture, you will be seeing that the person gives more importance to the camera than his child. So it clearly shows that he doesn't have any priorities. So we need to give priorities, and SAE J1939 helps us to give priorities, and this is how a prioritized message looks from the less important messages. So this is the Motorhawk CAN send block. So we'll be giving information about start bit value, offset, bit line by using MATLAB script. And we should make a note that J1939 uses Little Indian format. So by this time, we assumed that we have collected necessary information to build up a model. So we went ahead and built our model, and just like a real world scenario, model should be tested before it is being into production. And my friend Samant will be talking about the testing procedures. Thank you.
Thank you. Good afternoon, everyone. My name is Samant. I'm a master's graduate in electrical and computer engineering from Indiana University, Purdue University, Indianapolis. So right now I'm going to talk about DTE and conclusion. Once our model is built and ready, our model is ready and we need to test it somewhere before testing it on the engine. So we have a platform, desktop testing environment where we built our model and where we built the model which we built, we tested on this. It didn't matter with us. Even though it was a safer environment, we broke the engine several times. We gave it a hard time. So yeah, what basically desktop environment is, it is hardware and loop testing, where you get a replica of an engine. So the model which we have generates signals which is similar to the engine, Cummins engine which we have. So, and our model by which we can verify our model. So this is basically done by DTE. So once we have done with DTE, I want to conclude this presentation. So before coming to this LHP, we were like confused, what are we going to learn? We just had a clarity that we are going to run a diesel engine, but we don't know how we are going to do that exactly. So there were several series of steps which are given by LHP, and there were several requirement and design things which are given by LHP, and they were very on target that we were able to understand each and everything in proper, because we had different teams at different times, so we were able to build a team. We were able to act as a team in each and every point of the time. So first thing which we did was we did the requirement analysis and tried to design how the model should look like. And then one more important thing which we did was documentation and issue tracking. So whenever we built a model, as I previously mentioned, we changed teams at each and every point of time. So the thing was we were not able to discuss previous team's model with the other team. So this document analysis and issue tracking helped us in that thing. So we were able to, even though we were in the middle of building our model, we were building it from scratch in each and every point of time. So this helped us a lot. So, and after the building of the thing, we were doing integration testing, and we had a regular team meeting and lunches, which helped us, become more as a team. So we became as a team by the end of the course.